Okay, this video is going to be on how to get started and solve some of these problems on the circular motion worksheet. Feel free to skip ahead if you need to. I'm just going to say all these questions. You can just look at my solutions and you can figure them out. That's fine. Let's just jump into these free body diagrams down here. See if I can get this focused a little bit better. That's okay. So draw an FBD for a ball swinging on a string in a vertical circle. Ignore gravity for this problem. Which force is the centripetal force? So here's a ball swinging on a string, and I just say ignore gravity here because I just don't want to put in the gravity force. But so the only force that's acting on the ball is a tension force, and that's all that you're going to draw in the free body diagram. It kind of depends on what the angle is, like whether you're drawing the ball from up here or down here or whatever it is. So whichever way you're doing it, you're going to draw the ball like this, and then there's just going to be a force of tension acting on it. Or it could have been like this, and the tension could have been here, or like this, and the tension could have been there. Whichever direction it's going, there's just tension. Tension is the centripetal force, that's it. Okay, over here, a car going around a corner. The best way to draw this is, rather than drawing the car from above like this, we're going to draw the car coming straight out like this at you, turning this way or turning that way. So we're drawing the car from this perspective. There's the car, right? We're going to have gravity going down. We're going to have a normal force going up. Those are balanced. And then if the car is going this way, then we're going to draw a force going this way, and it's actually friction that's keeping the car going around the corner, and friction is the centripetal force in this case. Okay, next page. Child on a merry-go-round at a playground. So same thing here. If we're drawing a top-down view, it doesn't really work, so we're going to draw a view of, here's my child, on the merry-go-round coming at us this way, so facing this way, and on the merry-go-round, and the merry-go-round sort of turning like this, perhaps, or maybe it's going this way. We'll make it turning this way. So it's going to look real similar to the last one, where there's the child, gravity and normal force are going to balance each other out, and it's going to be a friction force holding them on the merry-go-round, pointing towards the center of the circle. Or maybe it goes this way. Good? Let's see, person walking inside a rotating space station, artificial gravity. Let's see if I can find my rotating space station. So here's my rotating space station. Remember, people are walking around on the inside of this. So here, if this paperclip was a person, they would be stuck to the inside of this right there. And there's going to be a normal force pushing on them towards the center of the circle. And that's going to be their sense of gravity. So once again, it could go in a lot of different directions. It could go here like that. It could be down or something. But remember, if you're in space and there's artificial gravity, there's not really like an up or a down or anything like that. So let's see. Okay, that's looking okay. So that's it. And then the normal force is the centripetal force. Oh, I forgot over here, the friction force is the centripetal force. Riding a Ferris wheel at the top of the circle. So we're going to have gravity going down, and there's going to be a normal force going up. The normal force is going to be slightly less than gravity. Gravity is the centripetal force pointing towards the center of the circle, but it's kind of battling against normal force here, and there needs to be a net result of these things down towards the center of the circle. So normal force has to be a little bit less than gravity. Like, for example, just throwing some numbers, if that were 100 newtons, maybe this would be 90 newtons, and my net force would be 10 newtons in the downward direction, and that would be towards the center of the circle. So here's the Ferris wheel coming up like that. You need a force pointing towards the center of the circle, and it's going to come from gravity. Person on a roller coaster loop upside down at the top of the loop. Which force is the centripetal force? So this time we've got gravity going down, and we've got a normal force going down also. So if you're upside down in the loop like this, there's a normal force pushing you down. Now the size of this normal force could change depending on how fast you're going. If you're going really fast, the normal force gets really big. If you're going slower, the normal force could be smaller. You could potentially have a situation where you have no normal force, in which case you'd feel a sense of weightlessness at the top. Okay, just to keep things moving here, let's move on to these problems. So we have, see if once again if I can get that to focus a little bit better. Yeah, it's okay. So in this problem, you're given the velocity and you're given the acceleration and you're trying to find the radius. So we're working with this formula. Good. And you're given the acceleration in g's. So remembering that 3 g's is going to be equivalent to 30 meters per second squared. So that's what we're going to plug in for centripetal acceleration here. I like to maneuver this with algebra first and solve for the variable and then plug the numbers in. So if I rearrange this equation, I can say R equals AC over, did that the wrong way, sorry. V squared over AC. There we go. So that's what I'm looking for. And then I just plug in my numbers. 25, don't forget to square it, divided by my acceleration, which was 30. And then you'll get a number for that. It's on my solutions. For this one, soccer player running around, finding the centripetal acceleration. So we're just using this formula, V squared over R. We're given the V and we're given the R. So we just got to pop those in. Don't forget to square the velocity, 1.5. And you'll get a number for this. I forget what it is. And then to express it in G's, just divide by 10 to express it in G's. For this one, if you feel like you're getting pulled to the outside of the ride with a force of half your weight, that means that your centripetal acceleration is half of a G. That's what that means. You're getting pulled to the outside with a force of half your weight. If you were getting pulled to the outside with a force of 2 times your weight, then that would be 2 Gs. Or 3 times your weight, then that would be 3 Gs. So a force of half your weight is half a G. And half a G is going to be 5 meters per second squared. So we're looking for the velocity. So we have this. Rearranging it, velocity is going to be the square root of AC times R. So now we just plug in our numbers. Square root of, there's our acceleration, 5, and the radius is 8. And you'll get a number for that. I think in my solutions I had meters for the answer, but it should be meters per second. And square root of 40. And then this mass was sort of a little bit irrelevant. There's a way to solve the problem using forces, but I think this way works out just fine. Okay, moving right along. Let's see here. We've got, okay, so RPMs to velocity is sometimes a little bit tricky, so just note that there's a formula for that. So we got a tennis ball swinging in a horizontal circle. The string has this length, and there's the mass of the ball. And we're going to ignore gravity for this problem. So we got just a horizontal circle here. Tension is pulling the ball in. So tension is the centripetal force, right? So if we draw a free body diagram, there's the ball. There's force of tension going one way. And this is the centripetal force. So I know that tension is the centripetal force. I also have a formula for centripetal force, which is mv squared over r. And we just have to plug in the numbers. 350 grams is going to be 0.35 kilograms, and 75 centimeters is going to be 0.75 meters. Make sure that those are good. This is M, and this is R. Well, sometimes it's tricky, by the way, because M stands for mass and it also stands for meters, so, just got to know what you're doing. And then to find the V, we're going to take 2 pi times the radius divided by 60, multiply that times the RPMs. So you're given the RPMs, boom, there's radius right there, 2 pi divided by 60, so you'll get a number for this. And then that number is going to go in, there for velocity, and then the mass goes in there, and the radius goes in there, and then you just figure out what this equals. Okay, if the length of the string is doubled, but the RPMs stay the same, what's the tension in the string? You'll need to recalculate the velocity. So you have to recalculate the velocity because our velocity formula is 2 pi r over 60 times your RPMs. So this time the length of the string is doubled. So now your R is going to go to 1.5 meters. And you have to recalculate what your velocity is. Once you recalculate your velocity, then your force is still just mv squared over r. So whatever this equals goes in there. There's your radius, and then it's the same 0.35 kilograms that goes in there. So interestingly enough, if you wanted to just use some variables, you'll notice that the r factor goes in the numerator squared, and then it's in the denominator here, so it'll kind of cancel out one of the r's. So anyway, that's how you'll sort of see how that problem's going to work. Or just do it the way that I have it up here. Okay, so in this situation, you get shrunk down, there's your mass, there's your radius, and there's your RPMs. How much centripetal force do you experience? So that's just this, mv squared over r. You're given your mass and your radius, and once again, to find your velocity, you'll just do this to find your velocity, plug all those numbers in, and then you'll get something here. To find the coefficient of friction, I'm just going to say skip this for now. We just didn't do enough with friction during the time when we talked about forces to really understand what's going on here, and I don't want to double back and redo it. Okay, so now we're talking about vertical circles and loops. So for this first problem here, didn't quite give you enough space to work, so I'm just going to use a separate piece of paper over here to sort of show what's going on. So on this one, you have a dog. It's on a swing at a playground. The swing has a radius, and we know the dog's mass. We're finding the normal force on a dog. So drawing the free body diagram, it's going to look like this. We're going to have gravity going down, and we're going to have a normal force going up. Now, the normal force has to be bigger than gravity because we're going in a circle in this direction. We need a net force in the vertical direction. Force of gravity, by the way, is just m times g. I get a lot of people saying, oh, the force of gravity is just 10. Well, if that were the case, then everything would have a weight of 10, which doesn't make sense. So to find the force of gravity, you need to take the mass and multiply it by 10 for g. So that's going to be 15 kilograms, given in the problem, times 10. That's 150 newtons right here. Now we have to find the normal force. In order to find the normal force, we actually have to figure out first how much centripetal force do we need on this dog. So let's do a little side quest here, and let's figure out how much centripetal force do we need. mv squared over r. So that's 15, and 5 is the velocity. 5 squared divided by 5, and then this turns out to be 75 newtons. So you need 75 newtons of centripetal force. We've got this pulling down, so this minus this has to equal 75 total. I need a net force of 75 in the upward direction to be my centripetal force, right? So if I have a net result of 75, 150 down, then this one must be 150 plus 75. So this one must be 225 newtons, right? So when I take this minus this, then I get my 75 newtons overall. So there's my normal force. Once again, if you want to write it on an equation, then you have normal force minus gravity equals centripetal force, right? And then this, oops, that's not equals, that's a minus. Minus 150, already figured that out here, equals 75. So your normal force has to be 225 newtons. Okay. Snowboarder moving through a half pipe, thought of a semicircle, and so on. The snowboarder is 3 g's at the bottom. Find the velocity of the snowboarder. Okay, so the easy way to, let's see how I want to say this. The way that I did it in the worksheet solutions is totally fine, but in essence, if you're experiencing 3 g's, sometimes you want to take gravity into effect, but let's just not take gravity into effect here. So what I'm saying is, if you're doing 3 g's, then that's 30 meters per second squared. That's going to be your centripetal acceleration, which is v squared over r. And if I'm going to find v, we sort of did this on the last page, it's just centripetal acceleration times r, square root. So that's going to be square root of 30 times 4 meters is the radius. And you'll get an answer out of it. And that'll be fine. And that'll be in something times something in meters per second. Okay, on the next run, the snowboarder has twice the speed. How many g's will they experience? Well, because our formula has v squared over r, twice the speed means 4 times the number of g's because you're going to square that velocity. Okay, and lastly down here in terms of these positive, negative, and 0 g's. So the idea is if you're falling straight down or more or less straight down, that's going to be 0 g's. So you don't have any normal force acting on you. I guess there's a little bit of an angle here, so it might not be exactly 0 g's, but that's sort of what I meant by here is 0 g's. Neutral g's, by the way, is just when you're over here at this situation, which means it's really like 1 g, one normal sense of gravity in the downward direction. Now when we have dips like this is always going to be positive g's in here. You're feeling really heavy, the acceleration is towards the center of the circle like that. Over here, this is also going to be positive g's because you're going, the acceleration is towards the center of the circle. You're going to feel heavy right there. You're going to be stuck in your seat and feel really heavy. For this situation, it could be a couple of possible things. First of all, it could be negative g's. if you're going really fast over the top of this hump, then you're going to need something that's holding you into your seat, like a strap or a seatbelt or something like that. Otherwise, you might go flying out of your seat. So if you're being held down by something that's pushing you down, that's going to be negative G's. It could also be 0 if you happen to be going at just the right speed, so that gravity acts as the centripetal force right here, then you're going to feel momentarily weightless right here. You're going to feel like you're sort of floating out of your chair. And I think you can get the sense if you've gone over a bump in your car and you felt like, woo, right? You probably didn't go weightless in your car, but you got a little bit of a sense of your normal force decreasing. So if you got the right speed right here, then you could get the normal force to go to 0. You could potentially have a neutral right here if you were just kind of driving along at a really slow speed, but that's not really what's going to happen in a roller coaster. This is a roller coaster. And then this one right here, it's a little hard to tell what I was doing in the drawing, but I kind of meant for it to be a little bit of a circle kind of going this direction. So this could potentially be negative. It could also potentially be neutral if you're just kind of cruising along at like a regular speed. You know, you're not really going too fast or too slow. So negative, neutral, you could theoretically maybe be 0 G's at this spot as well. So a quiz question on this is going to be pretty tricky. I'll be real specific about it, probably asking you for either positive G's or negative G's or something like that. Okay, hopefully that's helpful.